and welcome to the Deep Dive. We take complex topics, unpack them, and give you, well, the essential nuggets so you can get up to speed fast. Today we're tackling something really fascinating. It's at the heart of so much modern computing speed. NVIDIA's CUDA platform. Yeah, if you've ever wondered how GPUs manage to power everything from, cutting-edge AI to those incredible video game graphics, well, this deep dive is definitely for you. Our goal today, to demystify CUDA. It's NVIDIA's platform for parallel computing. Think of it like a special language that lets you unlock the supercomputing power hiding inside your graphics card. We'll explore the big shift in thinking you need for GPUs, walk through a typical CUDA program, look at how all those parallel threads get organized, and really dig into the critical role of memory. Plus, we'll touch on some advanced optimization tricks, useful libraries that can save you a ton of time, and the essential tools for debugging and figuring out if your code is actually running fast. All our insights today come from two really comprehensive sources: CUDA Essentials, Programming, Optimization, and Tools, and the developer's roadmap to CUDA proficiency.
So by the end, our mission is to equip you with the core ideas, the optimization secrets, and the tools you need to really grasp how GPUs just crunch numbers at these speeds that honestly blow traditional CPUs out of the water. Okay, so let's dive into that first big shift. When you think about a standard computer, you're usually thinking about the CPU, right? The central processing unit. It's like that brilliant, super focused chef, maybe doing one complex task at a time, but doing it incredibly well. But GPUs are a whole different beast, aren't they?
Oh, absolutely. A completely different beast. And this gets us right into what's called the heterogeneous computing paradigm. It sounds fancy, but the idea is pretty straightforward. You're essentially using different types of processors together, each one optimized for what it does best. So the CPU, which in the CUDA world we call the host, it's really good at sequential stuff, tasks that are sensitive to latency, how quickly you get the first result back. It manages the overall program, handles I/O, that kind of thing. The GPU, on the other hand, we call that the device, is all about throughput. It's designed for massively data parallel work. So instead of, say, 4 or 8 really complex cores like a CPU, a GPU might have thousands of smaller, simpler, but very efficient cores. These cores can all perform the same operation, but on different pieces of data, all at the exact same time. Think matrix multiplication or figuring out the color of millions of pixels on your screen. Perfect for the GPU. Yeah, the analogy I like is this: CPU is the conductor of the orchestra, making sure everything flows correctly. But the GPU, that's the entire orchestra, with every instrument playing its part simultaneously.
That orchestra analogy really works.
Yeah.
Okay, so CPU is the conductor, GPU is the orchestra. How do they actually work together in a real CUDA program? What does that dance look like?
Right. There's a definite pattern, a kind of choreography. A typical CDA program follows this host device workflow pretty closely. Usually you start on the host, the CPU side. You allocate memory, just normal RAM, and you initialize your input data there. Then the next step is crucial. You allocate corresponding memory buffers over on the GPU and its own dedicated memory, the VRAM. And step 3, you have to explicitly copy your input data from the host's RAM across to the GPU's VRAM. There's a function for that, cuda-gdb, where you tell it you're going from host to device.
Got it. So data's got to move over first.
Exactly. Once the data is sitting on the GPU, the CPU then launches a special parallel function, we call this a kernel, onto the device. This kernel is where the thousands of GPU cores do their parallel magic. After that kernel finishes crunching all the numbers, you copy the results back from the GPU's VRAM to the host RAM. Again, usually with cuda-gdb, but this time specifying device to host. And finally, back on the CPU, you can use those results for whatever's next, and then you clean up, free the memory you allocated on both the host and the device.
Okay, that makes sense. Allocate, copy over, compute, copy back, cleanup. But you mentioned copying data back and forth. That sounds like it could be slow. Is that usually the main bottleneck? Where does performance often get tripped up?
You hit the nail on the head. That is very often the single biggest performance killer. Those data transfers between the host and the device, specifically across the PCI Express bus, the PCIe bus, compared to how fast the GPU can access its own memory, that PCIe bus has much lower bandwidth and much higher latency. It's like trying to funnel a river through a garden hose. It creates this major serial bottleneck in your otherwise parallel computation.
Ah, okay. So even if the GPU computes lightning fast, getting data to and from it can slow everything down.
Precisely. So a fundamental principle, maybe the core principle of high-performance CUDA programming, is to minimize that host-device communication. You want to do as much work as possible on the GPU, maybe chain several kernels together, before you absolutely have to bring the data back to the CPU. Keep the data resident on the GPU as long as you can.
Okay. Minimize the back and forth. Got it.
Yeah.
So let's say we've moved our data over.
Now, how do we actually tell those thousands of GPU cores what specific piece of work they should be doing? How does CUDA manage all that parallelism?
Right, you've got this army of cores. How do you organize them? CUDA uses a really elegant two-level hierarchy. And this hierarchy maps very nicely onto the physical hardware of the GPU, which is why it's so efficient. At the very top level, when you launch a kernel, you define a grid. The grid basically represents the entire scope of your parallel problem for that specific kernel launch. It contains all the threads you're going to run. And this grid can be organized in 1, 2, or even 3 dimensions, which is handy for working with, say, 2D images or 3D volumes.
Okay, the grid is the whole job. What's inside the grid?
Inside the grid, you have thread blocks. A thread block is a group of threads. You can have up to 124 threads in a block, typically, and they are scheduled to run together on a single physical unit on the GPU called a streaming multiprocessor, or SM. Now, the key thing about threads within the same block is that they can cooperate. They can share data using a special, really fast type of on-chip memory called shared memory. We'll talk more about that later. And they can also synchronize their execution. There's a function, sync threads, that acts like a barrier. All threads in the block have to reach that point before any of them can continue.
Ah, so blocks are like little teams that can work closely together.
Exactly. Mini teams is a great way to put it. But, and this is critical, threads in different blocks generally cannot directly communicate or synchronize with each other easily. They run independently. Blocks, just like grids, can also be 1D, 2D, or 3D.
Okay, grids contain blocks, blocks contain threads. And I keep hearing the term warp. What's a warp in this picture?
Ah, yes, the warp. The warp is the fundamental unit of scheduling on the SM. A warp always consists of exactly 32 threads. And here's the magic, or rather the architecture. All 32 threads within a single warp execute the exact same instruction at the same time, but they operate on different data. This execution model is called SIMNT single instruction, multiple thread. It's incredibly efficient for the hardware. One instruction, fetch, decode, and dispatch, serves 32 threads.
Single instruction, multiple threads, SIMNT.
So this whole hierarchy, the grid, the blocks within the grid, and the warps of threads within the blocks allows the CUDA runtime system to manage this massive number of logical threads and efficiently schedule them onto the limited number of physical SMs on the GPU. As one block finishes its work on an SM, the scheduler can immediately swap in another waiting block, keeping the hardware busy and maximizing throughput. And crucially, to make this all work, each thread needs to figure out which piece of data it's supposed to process. UDA gives you built-in variables like griddim, the size of the grid, blockdim, the size of the block, block-edx, which block am I, and thread-pythonx, which thread am I within my block. Using these variables, each thread can calculate its own unique global index, like its address within the overall problem. For example, in a simple 1D case, the global index is often just block-idx.x, blockdim.x, plus thread-itx.x. That tells the thread exactly which element of an array, for instance, it should work on.
Wow, okay. It's like a highly organized coordinate system for this massive parallel workforce. That makes sense. Now, we've touched on memory being critical. You mentioned shared memory within a block being fast and global memory being slow. Can you break down that memory landscape inside the GPU a bit more? What are the different types, and why is managing them so vital for performance?
Absolutely. This is arguably the most important aspect to understand for getting good performance. Performance in CUDA is overwhelmingly dictated by how well you manage memory access. It's often not the raw computation speed, but the memory speed that limits you. Your ability to sort of orchestrate data movement between these different memory spaces, that's really the key skill. The goal is always, always, always keep the data your threads need in the fastest possible memory space for as long as possible. Maximize reuse, minimize trips to the slower memory.
Right, so what are the options? What's the hierarchy?
Okay, so at the very top, the fastest, you have registers. These are super fast on-chip memory locations. Each thread has its own private set of registers. They're read-write, and the compiler tries its best to use them for your local variables, loop counters, intermediate calculations. You don't usually manage them directly, the compiler does.
Okay, registers are fastest, private to a thread. What's next?
Next down is shared memory. This is also very fast on-chip and read-write, but unlike registers, its scope is limited to a single thread block. This is memory you do manage explicitly in your code. You declare it using the shared keyword. It's absolutely crucial for allowing threads within a block to share data quickly and cooperate, like we talked about before. Think of it as a user-managed cache for the block.
Shared memory for block-level cooperation. Got it.
Then there's constant memory. This is also on-chip cached, but it's read-only from the GPU kernels. Its scope is per grid, meaning all threads in your kernel launch can potentially access it. It's best for data that doesn't change during the kernel and is read by many threads, like, say, filter coefficients or physical constants. If all threads in a warp read the same address from constant memory, it can be very fast because the hardware can broadcast that value.
Okay, read-only, good for broadcast. What about the big one?
Right. The big one is global memory. This is the largest memory space on the GPU. It's the GPU's main DRAM, located off-chip. It's accessible by all threads in the grid, and it's also the memory space that the host CPU can read from and write to using those CUDA-gdb calls. But it's also the slowest by far. Accessing global memory inefficiently is the #1 reason for poor CUDA performance. This is where you use CUDA-malloc to allocate space.
Slowest but biggest, and how we get data on and off the GPU.
Okay.
Is that all?
There's one more you might encounter called local memory. Now, confusingly, local here doesn't mean fast or on-chip. Physically, local memory actually resides in the slow off-chip global memory. It's logically private to each thread, but the compiler uses it automatically as a fallback, mostly for when a thread needs more registers than are physically available. That's called register spelling, or sometimes for complex data structures like arrays where the index isn't known at compile time. If you see local memory usage showing up when you profile your code, it's often a sign that something's not quite optimal because it means threads are hitting that slow global memory unexpectedly.
Okay, registers, shared, constant, global, and local.
Yeah.
Which is really just slow global memory used automatically. Wow, quite a landscape.
It is. And navigating it effectively and making smart choices about where data lives and when it moves, that's the game. That's where you unlock the GPU's potential.
So knowing about this memory maze is one thing. How do we actually use that knowledge? What are the key optimization strategies to make our code, fly? Especially regarding that slow global memory.
Right. Let's talk tactics. Since global memory is often the biggest bottleneck, optimizing access to it is usually priority #1. The most crucial concept here is memory coalescing. Remember warps? Those groups of 32 threads executing in lockstep.
SCMT.
Exactly. Memory coalescing happens when all 32 threads in a warp access locations in global memory that fall within a single large naturally aligned memory segment. When this happens, the hardware can grab all the data those 32 threads need in one single, highly efficient memory transaction. Boom, fast. But if the threads in a warp access scattered memory locations or locations with a large stride between them, the hardware has to issue multiple, separate, much less efficient memory transactions. That kills your bandwidth and your performance. We call that uncoalesced access.
So you want threads in a warp to access memory locations that are close together and aligned.
Precisely. A classic example where this comes up is matrix transpose. If you write it naively, say reading row-wise from the input matrix, that might be coalesced. But then when threads write column-wise to the output matrix, those writes will likely be horribly uncoalesced.
Ah, right. Because threads in a warp are writing far apart in memory.
Exactly. So the standard optimization uses shared memory. First, the threads in a block cooperate to read a small tile of the input matrix from global memory into fast shared memory. They do this read in a coalesced way. Then you use that sync threads barrier to make sure all the data for the tile is loaded into shared memory. After the sync, threads read the data they need from shared memory, but with transposed indices. Accessing shared memory is fast, remember. And finally, they write the transposed data from shared memory back out to the output matrix in global memory, again, ensuring the writes are coalesced.
Okay, so shared memory acts as a staging area to rearrange the data access pattern.
You got it. You transform two potentially uncoalesced global memory accesses into two coalesced global accesses, plus some very fast shared memory accesses. The performance difference can be huge.
That makes sense. Now, you mentioned shared memory is fast, but are there pitfalls there too? What about these bank conflicts you hinted at?
Ah, yes. Shared memory is fast, but not infinitely flexible. It's physically divided into, typically, 32 memory banks. Think of them like 32 parallel lanes to access the shared memory. A bank conflict occurs if two or more threads within the same warp try to access different memory addresses that happen to fall into the same bank at the same time.
Like multiple cars trying to merge into the same lane simultaneously.
Perfect analogy. The hardware can't service those requests simultaneously, so it has to serialize them. One thread goes, then the next, which obviously slows things down considerably. It negates the parallelism you were hoping for from shared memory.
And when does this typically happen?
A common case is in parallel reduction algorithms where threads access shared memory with a stride. If that stride happens to be a multiple of 32, the number of banks, then all threads in a warp might end up trying to access addresses that map to the same bank. Collision.
So how do you avoid that?
Often, a simple trick works: padding. You can add a little bit of extra unused space to your shared memory array declaration. For example, if you have a 2D tile in shared memory, maybe shared float tiledim, you might change it to shared float tiledim +1. Adding that one extra column can change the mapping of addresses to banks just enough to avoid the conflicts for common access patterns.
Huh. Just adding a little padding can fix a traffic jam. Clever.
It often does the trick. It seems small, but it can make a real difference in shared memory throughput.
Okay, so we've talked optimizing memory access. What about hiding latency? Especially the latency of, say, copying data from the host, or even just waiting for a kernel to finish before starting the next step. How can we make the GPU multitask?
Great question. This is where CUDA streams become really powerful. By default, if you just launch a kernel, then do a memory copy, then launch another kernel, they usually happen sequentially relative to the GPU. Kernel 1 finishes, then the copy starts, copy finishes, then kernel 2 starts. This happens in the default stream. But CUDA streams let you create multiple independent queues of work for the GPU. You can put, say, a memory copy operation in stream 1 and a kernel launch in stream 2. The magic is that the CUDA runtime and the GPU hardware can then try to overlap the execution of operations from different streams. So while the data transfer for stream 1 is happening over the PCI bus, the GPU's compute units could be busy executing the kernel from stream 2.
So you can hide the transfer time behind useful computation.
Exactly. You keep the GPU busy doing multiple things concurrently. However, for this overlap between host-to-device or device-to-host copies and kernel execution to actually work reliably, you generally need to use pinned memory or page-locked memory on the host side.
Pinned memory, what's that?
Normally, the operating system is free to move pages of your application's memory around in physical RAM. But for asynchronous data transfers, the GPU needs to know the physical address of the host memory won't change while the transfer is in progress. So you allocate pinned memory using a special function, like cuda-malloc-host. This tells the OS, don't move this piece of memory. It allows the GPU's DMA engine, direct memory access, to transfer data asynchronously without the CPU's constant involvement. Then, when you launch kernels or issue memory copies, you can specify which stream they belong to, usually as an extra argument. cuda-malloc-async is the function for asynchronous copies. You can also use CD events to manage dependencies like, don't start this kernel in stream 2 until this copy in stream 1 is finished.
Okay, so streams plus pinned memory plus asynchronous copies enable real concurrency on the GPU. Very powerful.
It's fundamental for getting maximum utilization out of the hardware in complex applications.
One more potential hazard with all these threads running wild. What if multiple threads try to update the exact same memory location at the same time? Like, imagine multiple threads trying to increment the same counter. What stops it from becoming a total mess?
Yeah, that's a classic race condition. If multiple threads read a value, increment it, and write it back without any coordination, the final result will likely be wrong, and it might even be different each time you run the code. It's non-deterministic chaos.
So how do you prevent that? Locks. Mutexes.
CUDA provides a hardware-level solution: atomic operations. An atomic operation is guaranteed by the hardware to execute as a single, indivisible, uninterruptible unit. It performs a whole read-modify-write sequence without any other thread being able to jump in the middle. So for incrementing a counter, instead of ptr-else +1, you'd use a function like atomic add, ptr1. CUDA provides atomics for addition, subtraction, min, max, bitwise operations, and a crucial one called atomic access, compare and swap, which is a building block for more complex synchronization.
Okay, atomic operations guarantee safe updates to shared locations.
Yes, they ensure correctness. A common use case is building histograms. Multiple threads might need to increment the counter for the same bin. Atomics prevent lost updates. However, atomics aren't free. If many threads in a warp or across different warps are constantly trying to perform atomic operations on the exact same memory address, those operations get serialized by the hardware. You lose parallelism, and performance can suffer significantly.
So they solve the correctness problem but can introduce a new performance bottleneck.
Exactly. So a common optimization strategy is, for instance, to have threads within a block perform a reduction or accumulation into fast shared memory first, which doesn't necessarily need atomics if done carefully, and then have only one thread from each block perform a single atomic operation to update the final result in global memory. This dramatically reduces the contention on the global atomic.
Minimize the number of atomic operations to global memory.
Makes sense.
Yeah.
Okay, this is a lot of detail. Coalescing, bank conflicts, streams, atomics. It sounds like getting peak performance requires some serious effort and expertise. When should a developer, maybe, not try to reinvent the wheel and write every kernel from scratch? Are there pre-built solutions?
That's a really important point. Yes, absolutely. While understanding these concepts is crucial, you don't always need to handwrite every low-level kernel. NVIDIA provides a suite of fantastic, highly optimized, accelerated libraries for common computational tasks. Trying to beat the performance of these libraries for standard problems is, well, it's extremely difficult. They encapsulate years of expert tuning. Using them is often far more productive and yields better results faster.
Okay, so what are some key libraries developers should know about?
I'd highlight three main ones to start. First, cuda-gdb. That's the CUA Basic Linear Algebra Subroutines library. It's for dense linear algebra, matrix vector multiplication, matrix-matrix multiplication. The matrix-matrix multiply function, cuda-gdb for single precision, is probably one of the single most heavily used functions in all of GPU computing. If you need linear algebra, look at cuda-gdb first.
Linear algebra is everywhere. What else?
Second, CoFFT. This library handles fast Fourier transforms, which are essential in signal processing, image analysis, scientific simulations, and more. It's designed to be similar in usage to the popular CPU library FFTW. You typically create a plan for a specific FFT size and type once, and then you can execute that plan very efficiently many times on the GPU.
Okay, FFT's covered. And the third?
Third, I'd mention Thrust. Thrust is a bit different. It's a C++ template library that provides a high-level interface, very similar to the C++ standard template library, STL, but for parallel algorithms executed on the GPU. So you can do things like thrust.sort, thrust.reduce, thrust.transform on data stored in GPU memory, often with just a single line of code. It abstracts away a lot of the low-level kernel writing details, prioritizing developer productivity, while still delivering excellent performance for many common parallel patterns.
The sort, reduce, scan,
Yeah.
like parallel building blocks. That sounds incredibly useful.
It really is. It lets you focus more on the algorithm logic and less on the CUDA boilerplate for many tasks.
Now, what about the Python world? A lot of data science, AI, and scientific computing happens in Python these days. Can Python developers tap into this CUDA power easily?
Oh, absolutely. The Python ecosystem for GPU computing is thriving. There are several great options. Probably the most direct equivalent to NumPy is CuPy. CuPy aims to be a drop-in replacement. For many NumPy operations, you can literally just change your import statement from import NumPy as NP to import CuPy as KeyP, and your array computations will run on the GPU. It's fantastic for getting started quickly if you know NumPy.
Wow, just change the import. That's slick.
It often works surprisingly well, yeah.
Yeah.
Then there's Numba. Numba is a JIT, a just-in-time compiler. It can take standard Python functions, especially ones with loops that operate on NumPy arrays, and compile them down to optimize machine code, including generating CUDA kernels directly from a subset of Python syntax using special decorators like at cuda-gdb, so you can write GPU kernels in Python.
Write kernels in Python. That's cool.
It is. It lowers the barrier to entry quite a bit. And finally, if you need the most direct fine-grained control, there's PyCUDA. PyCUDA lets you write your kernels in C++, CUDA-SE, compile them on the fly from your Python script, and then launch them, managing memory allocation and transfers explicitly from Python. It gives you the full power, but requires managing more details yourself.
CuPy for NumPy users, Numba for GIT compiling Python to kernels, PyCUDA for full control. Lots of options for Python folks.
Definitely. Python is a first-class citizen in the CUDA ecosystem now.
Okay, so let's say you've written your CUDA code, maybe using one of these libraries, maybe you're writing your own kernel. Parallel programming is notoriously tricky to get right, let alone make fast. How do you debug this stuff? How do you figure out why it's not running as fast as you hoped? What are the essential tools?
Right. Debugging and profiling are absolutely critical skills. You can't optimize what you can't measure, and you can't fix what you can't find. NVIDIA provides a really powerful suite of tools for this, part of the Nsight family. For performance analysis, your first stop should usually be Nsight Systems. Think of this as the high-level system-wide profiler. It answers the question, where is my application spending its time overall? You run it alongside your application, like nsysprofile.myapp. It captures a timeline showing CPU activity, GPU activity, kernel executions, memory copies, API calls, all synchronized. It's great for spotting the big picture issues. Is the GPU idle waiting for the CPU? Are you spending way too much time copying data? Are your kernels themselves the bottleneck? Nsight Systems helps you identify where to focus your optimization efforts.
Okay, Nsight Systems for the big picture, finding the main bottleneck. What if it tells you a specific kernel is slow?
Then you drill down with Nsight Compute. This is the deep dive kernel profiler. It answers the question, okay, why is this specific kernel slow? You run it, targeting your application, maybe focusing on a particular kernel, like ankasset full ashoreport.myapp. It collects incredibly detailed hardware performance counters from the GPU while your kernel runs. The report it generates is gold. It has sections like GPU speed of light, which tells you if your kernel is limited by memory bandwidth or by computation. It shows occupancy, which is a measure of how well you're utilizing the SMs. It has detailed memory workload analysis showing cache hit rates, how well your global memory accesses are coalescing, and crucially, it often links these performance metrics back to specific lines in your source code. So you can see, this loop here is causing tons of uncoalesced memory accesses, or this calculation is limited by register dependencies.
Wow, connects performance metrics right to the source code line. That's powerful.
It's incredibly powerful for targeted optimization. Nsight Compute tells you why the kernel isn't reaching its potential.
Okay, so Nsight systems for where, Nsight Compute for why it's slow. What about correctness? What if the results are just wrong? How do you debug parallel race conditions or memory errors?
For correctness, the tool is cuda-gdb. It's an extension of the standard GNU debugger, GDB, that understands CUDA kernels and the GPU execution environment. It answers, why is my kernel giving me the wrong answer? You need to compile your code with debug flags -gu-g. Then you run cuda-gdb.myapp. It lets you do things you'd expect from a debugger, but on the GPU. You can set breakpoints inside your global kernel functions. When a thread hits the breakpoint, the execution pauses, and you can inspect the state of GPU memory, global shared registers. You can step through the parallel code. It even has commands to switch focus between different blocks, CUDA block, and threads, CUDA thread, so you can examine the state from different perspectives within the parallel execution. It's invaluable for tracking down race conditions, out-of-bounds memory accesses, or just logical errors in your kernel code.
Debugging parallel code with breakpoints and stepping. That sounds essential.
It absolutely is. Debugging parallel programs without a tool like cuda-gdb is painful, to say the least.
Okay, so a whole suite of tools. Nsight systems, Nsight Compute, cuda-gdb. Seems like learning these tools is just as important as learning the coding techniques.
I'd say so. They are your eyes and ears into what's actually happening on the hardware.
Now, putting all this together, the parallelism concepts, the memory hierarchy, the optimization techniques, the tools, what does real mastery look like in practice? The source materials mention several capstone projects. Can you give us a flavor of what those involve and what they teach?
Yeah, those capstone projects are designed to integrate everything we've discussed. They take non-trivial real-world problems and force you to apply these concepts holistically. For instance, one is high-performance 2D convolution, like for image filtering. This isn't just about writing the loops correctly. It heavily relies on using shared memory tiling effectively to maximize data reuse from global memory, minimizing those slow accesses. It directly tests your understanding of coalescing and shared memory management.
Okay, so convolution forces you to nail the memory strategy.
Exactly. Another example is parallel reduction and scan, prefix them. These are fundamental parallel building blocks, but achieving high performance requires careful attention to work efficiency, making sure every thread is doing useful work and meticulously avoiding shared memory bank conflicts during the communication phases. Then there's something like an n-body simulation, simulating gravitational forces between many particles. This often involves tiling, again for data reuse, but also pushes hard on optimizing the arithmetic calculations themselves, making sure you're getting good computational throughput alongside efficient memory access.
Computationally heavy, that one.
Very. And perhaps the ultimate capstone mentioned is optimizing GMM, general matrix multiplication, from scratch. This is a classic HPC challenge. The project takes you on an iterative journey. You start with a simple, naive, triple-nested loop implementation, which is terribly slow on a GPU. Then, step by step, you apply layers of optimizations. Global memory coalescing, tiling using shared memory, maybe even tiling for registers, using vectorized memory accesses, carefully avoiding bank conflicts, maybe loop unrolling. Each optimization builds on the previous one, and you use the profiling tools, like Nsight Compute, at each step to measure the impact and guide the next refinement. The goal is to see how close you can get to the performance of a highly tuned library like cublaz by systematically applying all these techniques. It really drives home how these optimizations work together.
Wow. That sounds like a serious undertaking, but an incredible learning experience, iteratively building up performance layer by layer.
It really encapsulates the whole process of CU development and optimization.
Well, this has been an absolutely fantastic deep dive into CDA. We've gone from the fundamental shift to parallel thinking with CPUs and GPUs, through the host device workflow, the thread hierarchy, navigating that crucial memory maze, to applying key optimizations like coalescing and using streams, leveraging the power of libraries like Kubernetes and Thrust, and finally using the essential tools like Nsight and cuda-gdb to debug and profile. You really have a solid foundation now.
Absolutely. And hopefully the key takeaway is that it's not just about knowing what these techniques are, like, use shared memory. It's about understanding why they work, the underlying hardware reasons, and how to apply them strategically based on what the profiler tells you. That's where the real performance gains come from.
So what does this all mean for you listening? Well, as computing leans more and more on specialized hardware like GPUs for acceleration in AI, science, graphics, everywhere, understanding these core principles of parallel execution, memory locality, bandwidth, it's becoming less of a niche programmer skill and more fundamental to understanding modern technology itself. The next time you use a sophisticated AI tool or boot up a visually stunning game, maybe you'll have a bit more appreciation for that silent, massively parallel orchestra working incredibly hard behind the scenes thanks to platforms like CUDA. And maybe, just maybe, you'll start thinking about problems you encounter, even everyday ones, in a slightly more parallel way. How could this task be broken down and tackled simultaneously? It's a powerful way to think. Thank you so much for joining us for this deep dive. Until next time, keep digging, keep learning, and stay curious.